Hello, in this video I want to talk about the chain rule. I'm actually quite surprised that I have yet to cover the chain rule on this channel, but yeah, without further ado I suppose, I want to talk about the chain rule, and really I just want to talk about three different forms of the chain rule that are really important to know, especially when we start getting into multivariable calculus and we start getting into even more basically introductions on differential equations and just stuff like that. This is just a really important skill. Chain rule is really quite powerful. So many proofs and derivations, they rely on it, and think of like implicit differentiation and all kinds of stuff. So this is one form of the chain rule. So let's start here. Basically what it's saying is it's just saying that if y equals some function of x, right, f of x, and that is raised to some power, so I denoted some power with n, it follows then that if you were to take the derivative, so dy by dx, right, the derivative of y with respect to x of this, or in other words, I'm using prime notation here, so y prime, first order derivative, what you're going to get is you're going to get n times your original function raised then to the n minus 1 power, and then that's going to be multiplied by f prime of x. Now let's just digest this a little bit. Like let's just focus on this part right here, this first part. Notice that this is just very basic property of differentiation that one will certainly learn right when they're introduced to the concept of differential calculus. Like let's just, instead of thinking of complicated functions, of composite functions or products or whatever, just look at something simple. Like let's just say we're given something like this, like y equals x raised, I don't know, to the 8th power, right? Well, if we were to differentiate this, right, just take the derivative, what do we end up? Well, it would follow that y prime would be 8x raised to the 7th power, right? Where one is taught that you bring the power down in front and you take 1 off the power. That's all that this is saying right here. This part right here of this first form of the chain rule. That's all it's saying. Now, the key then to the chain rule, and this is something that's perhaps one is inclined to forget when they're first learning it, I don't know, but the key part to the chain rule is that you have to then multiply this by your f prime of x, right? If you just do this part, that's not correct. That's not the chain rule. And in some cases, perhaps one might evaluate their function incorrectly, and maybe they end up just doing this part where you have to also multiply by your f prime of x. And I'll go over an example in just a moment. But before I get to that, I also want to just highlight a second form of the chain rule, and then we'll get to a third form, which is really important. But we'll get to that later. Okay, so the second form of the chain rule, which relates very much to the first form, and I like this because it highlights, most certainly highlights the concept of a composite function more explicitly than this form, where we've got, let's just say, like we've written above, if y equals, and I'll write it like this: if y equals f of g of x, right? This is a composite function. Very explicitly, we can say we can highlight the fact this is maybe a bit more explicit than other examples, but f of g of x. It follows then, if you take dy by dx, in other words, y prime, you're going to get something like this. If we just keep very general for the time being, you're going to get f prime of g of x. And then similar to this above, to what we've talked about, you're going to get, in this case, g prime of x. Right, and notice, like I said, this is a nice example because it just, I guess it emphasizes the notion of composite functions. It's a bit more explicit is what I'm trying to say when you look at this generally, maybe. Perhaps for some it's more explicit. Because like, notice maybe perhaps another common mistake will be to confuse composite functions in, I don't know, say you're given some other complicated function that's a product of two functions, right, where you would use the product rule, right? So f of g of x we describe this as being composite. In other words, it's a function of a function, and that's what the chain rule enables you to do. It enables you to differentiate a function of a function like this. But notice this is very different than writing, if we think generally again, f of x times g of x. This is the product of two functions being multiplied together, right? Where this is a composite function. This is a function of another function. And that's really what we're focusing on here, is this idea of a function of another function. But let's just work on an example. Let's just work on a very simple example. We'll get into all kinds of cool stuff later in other videos perhaps. But so in this case, let's just say we're given something like y equals 3x to the 4th power. And we'll add 1. Actually, let's just add it. We'll go plus x, and we'll raise all of this to some power, let's say 5. Alright, and now we need to differentiate this with respect to x. So what are we going to do? Well, we could write that, well, we're going to use a chain rule, aren't we? And so notice we'll just look at this first form of the chain rule. And so what we could say is that y prime equals, and we're going to, again, bring down our power, right? And then as it's written here, we're going to multiply it by our original function, which is 3x to the power of 4 plus x. And then we're taking 1 off the power, so that's going to be raised to the power of 4. And then we're differentiating our function, our f of x. In this case, it's everything inside the brackets. Everything inside the brackets. So that's going to be what? That's going to be 12x cubed plus 1. And that's exactly this result. This is exactly what we have up here. Now, another way to think about it, and this is how I personally like to think about it, when I'm given a very simple function like this, you know, and I have to take the derivative, what I would do is I would say, okay, y prime equals, I bring down my power, right, 5, bring it in front, and then I multiply that with the derivative of everything inside the brackets. So it'd be 12x cubed, as we found here, plus 1. And then I would set the original function minus n minus 1 power at the back. So it would be 3x to the power of 4 plus x to the power of 4. This is how I tend to think about it personally. It's perhaps force of habit. Just notice that it's just rearranged a little bit, right? But yeah, I just think it's I don't know. It's just a little bit more tidy to have your power at the back like that. But in any case, that's a good example, a very basic example of the chain rule in practice. But let's work on another. And actually, before we get to another, I'm going to introduce a third form of the chain rule. It's really important to understand, but also it's important to highlight that it's just a chain rule in operation. It might look a little bit different, but it's the exact same thing essentially. So I'll write it here. Third form of the chain rule, and here we're going to use Leibniz notation, and I'll explain why it's important in a moment. But what you want to do is, well, what it is, the third form is dy by dx, right? Our derivative of y with respect to x equals dy by some variable. We'll just set it to u. So dy by du. Many cases in practice in the future, the variable could be a function of time, whatever, right? So, but in this case, we'll just go dy by du times du by dx, right? Now, the reason I say this is important, it's important to think of the chain rule in this way as well, for a number of reasons. For example, when you get into multivariable calculus, so when you have more than one variable, notice we just have one variable here, right, our variable x. But you can have 2, 3, 4, you can have 7 variables. And so when we start to develop or expand on these ideas, the ideas in relation to the chain rule with just one variable to accompany functions with more than one variable, you'll notice the chain rule written using Leibniz notation, generally speaking. It would be presented in this way, and it's important to think about the chain rule also in this way. Also, for example, like when you get into, I don't know, think of something a bit closer here. So like connected rates of change, for example, things like that. It's really important to think in this way. And it's not formally, this isn't really formal, but in any case, like when you look at this, it is almost in essence like this du and this du cancels, right? When you multiply these together, so you get dy by dx equals dy by dx. But in videos on connected rates of change and stuff like that, I'll sort of highlight more of why that's relevant. But here, so this is the third form, and this is what we want to work with here in the second problem, and then we'll compare it actually with what we've already covered. So if I just kind of cut this page in half. Let's think of something. Let's say that we're given, I don't know, let's say we're given something like y equals 1 over 3 plus 2x. Okay, yeah, that's fine. So let's think through this method, or let's think through. We know we have to find the derivative here, and let's think about it using the chain rule with this form of the chain rule. So really, you won't need to write all of this out, but I'll just write everything out to make it explicit. What you want to do is you're going to want to set some variable to equal your function, basically, right? So 3 plus 2x here. So if we say, for example, we'll use u because we used it up here. We say let u equal 3 plus 2x. Well, it follows, right? If we let u equal 3 plus 2x, it follows that y equals 1 over u, right? Which this is just a very basic substitution. Well, if y equals 1 over u, this is the same equivalent to saying that y equals u raised to the negative 1 power, right? Because this is just basic exponent properties at this point here. And notice that in this statement, dy by dx equals dy by du times du by dx. We need to find our dy by du and our du by dx. Well, look what we've got here. We are able to do it. We can derive u with respect to x here in this part, and we can take the derivative of y with respect to u in this part, and then we can complete. We can fill in the components of this formula if you want to think of it like that. So let's do it. Let's take du by dx. And once we get, well, we're just going to get 2, right? We take du by dx here. And if we take dy by du, we're going to get, well, we bring down the negative 1, so that's just negative u, and then we take 1 off the power, so that's going to be negative 2. And then we're done. We can basically just fill this in now. So we can write, therefore, dy by dx equals dy by du. Well, our dy by du is just negative u raised to the negative 2 power. That's being multiplied by du by dx, which is just 2. Therefore, we can clean this up a little bit, and what we end up with is negative 2u to the negative 2 power. And then we just substitute back in for u, right? So we substitute back into u, which, when we've set u to equal 3 plus 2x, we just substitute back in. We're going to get negative 2 times 3 plus 2x to the negative 2 power. Okay, so we've used the chain rule successfully, and this is our result. Now let's compare that with the method, the form of the chain rule, I should say, that we used earlier. And can I make a bit of space? Yeah, I can probably fit it on this page. Let's just do it right here in this part of the page. And so let's use the form of the chain rule that we covered at the outset of the video. So in that case, we've got, as we know, we've got our y equals 1 plus 3, or 1 over 3 plus 2x. And if we were to take the derivative of y with respect to x, well, before we get to that, this is the same. This is how I would do it. I would say, well, y equals this. Okay, fine. This is the equivalent of saying that y equals 3 plus 2x raised to the negative, negative 1 power, right? Again, it's just basic exponent properties. And if this is true, we can just use the form of the chain rule that we covered, right? Because we can say, okay, y prime then, in this case, bring down our negative 1 power, right? We bring down the power, I should say, which is minus 1, and I'll write minus 1 to make it explicit. And then I would multiply by the derivative of everything inside the brackets, which we know is just 2. And then, of course, we want to reinsert our original function of x with the n minus 1 power, which is negative 2. And if you tidy that up, what do you get? Well, we get the exact same result that we got down here. And it's because we're doing the exact same thing, right? It's still the chain rule, as is this version. Just, I guess, a different way to think about it, maybe. It's just a different form. But you're essentially doing the same thing. It's the same operation. Okay, and then we got negative 2 times 3 plus 2x to the negative 2 power, exact same result as we got here. Yeah, so I think I'll probably end there. There's actually a fourth version of the chain rule, fourth form, I should say, and but I'll maybe save that for another time. It's just about taking the reciprocal. It's not too complicated, but might be worth covering.